So, if a state doesn't necessarily evolve in time, uh, what is it evolving in if it changes, or am I just not understanding this correct?
Yeah, so yeah, I'd say that's not the right way to think about it. Um, so to think about what a state is for in physics generally, what it's for from an operational point of view is you use it to help you make predictions. Okay, so you have this idea of a state at a given time, and you evolve it, and you might want to make predictions concerning something that happens here and something else that happens at a later time, and you can use the state as a tool to make those predictions. But if you have some different machinery that allows you to make predictions, then you don't need a state at a given time. You can choose this other machinery as well. So if you are able to replace the role that a state at a given time plays by some different mathematical machinery, um, then um, then you're in a good enough situation. Then you can make predictions, and at the very least, in physical theories, we want to make predictions. I realize I'm using the word predictions, and it's not quite the word I want because prediction has a sort of temporal sense to it. All I mean is when I use the word prediction, there is we have various bits of data, and we want to be able to calculate probabilities concerning that data. So, conditioned on this piece of data being true, what is the probability of seeing this other data over there? Those kinds of statements. So it's a very abstract. It was a very abstract endeavor in some ways, and of the various things I've done, that's the one that's hardest to really explain in any detail without getting into the math. It's a very abstract formalism, but it enables you to make predictions in the sense that I just explained, without having a state at a given time evolving forward in time.
So, in a way, this is like a reduction of possibilities.
Yes. Okay, that's a very good way of putting it. So the central tool I use in that approach is is exactly that, a reduction of possibilities. I call it compression. So so when you get this sort of data from different parts of your experiment, and you can imagine any data, any kind of data, and you can imagine it with any probabilities. But if you want to make some, if you want to do some useful physics, you want to start narrowing that down, and reducing the kind of amount of the data you would expect to see, and specifically making probabilistic predictions about that data. Um, so it turns out that you can do compression, which is where you narrow down the data in certain ways, and that's the basic mathematical trick that underlies the causal approach.
What are some next steps in your research? I've heard mention of a quantum equivalence principle. How does this provide a potential road forward?
Okay, so so I should so maybe I should first of all explain the Einstein's equivalence principle. This is from 1907. So in 1907, he realized there was this principle. He called it the happiest thought of his life because it was the 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 conceptual, the idea that led to general relativity. Not immediately. It still took him 8 years, and he was Einstein, so that was quite a while. But this was the key idea that led him to, to general relativity, and the equivalence principle, Einstein's equivalence principle, is this idea. You can imagine you're in an elevator, and the elevator is either falling freely, plummeting towards the Earth, or it's floating out in space. And imagine the elevator has no windows, so you don't know which situation you're in. Um, well, in either of those situations, if you have some objects like a ball, whatever, you have various objects around you. All those objects will be floating, appear to be floating. Now, in the case of the elevator that's out in space, they'll be floating in space with you. In the case of the elevator that's plummeting towards the Earth, they'll all be falling equally with you. Uh, but those two situations appear to be the same. They appear to be equivalent. So that was the equivalence principle. Um, and a different way of seeing that equivalence principle is that no matter where you are in the universe, you can always find a frame of reference where the laws of physics are inertial. By inertial, I mean things moving in straight lines. Um, and you can see it in those two cases. Either everything is moving in a straight line when you're in the elevator, when it's plummeting, all the straight lines are, viewed from the outside, it would be falling to Earth, but inside the elevator, it would just be straight lines of objects appearing to float inside the elevator. Or when you're floating, it's the same thing. So you can always find a coordinate system where you have inertial behavior. This is Einstein's equivalence principle. So now we go to quantum theory. Well, if you want to come up with a quantum equivalence principle, then you need a notion of quantum coordinate systems, um, and and that kind of idea was developed by Yakir Haranov, and co-workers back in the 1960s and 70s. He called it quantum reference frames. So um, you can imagine that the coordinates you use themselves are associated with quantum objects. Um, and so I took that idea of Aharonov's et al., and it's been worked on by other people more recently, um, Flaminia Giacomini and Czeslaw Bruckner and various other people. But I made it more suitable for the general relativistic context, where you really want to have abstract coordinates that live on a manifold. So the idea was to develop a quantum notion of coordinates. So that was the first thing. And then the second thing is, well, in quantum gravity, the thing you want to tame is indefinite causal structure. In Einstein, for developing general relativity, what Einstein needed to tame was the idea of non-inertial motion. And he found a way to tame that by showing that you could always find a coordinate system where the motion was inertial. And that played a crucial role in deriving his field equations. So in the context of quantum gravity, the thing you need to tame is indefinite causal structure. So the quantum equivalence principle, the idea of that is that there always exists a quantum coordinate system in the vicinity of any point such that you have definite causal structure. Okay, so it's very analogous to what Einstein did with the equivalence principle. You always have a coordinate system, so you have inertial behavior, but instead it's a quantum coordinate system, and you always have definite causal structure. And so my hope is that that principle could play a similar constructive role in developing a theory of quantum gravity to what the equivalence principle did in developing a theory, Einstein's theory of general relativity. That's the hope, and it's driven by this analogy that I described the problem of quantum gravity earlier. The problem of quantum gravity is to find a theory that reduces to general relativity and to quantum theory in appropriate limits. Well, Einstein was working on an analogous problem. His problem was to find a theory that reduces to Newton's theory of gravity or to special relativity in appropriate limits. And he solved that problem by finding the theory of general relativity. And he had to do that. He had to invent all sorts of new ideas. And he used the equivalence principle in doing that. And so you can try to pursue an analogous technique, develop tools which are analogous to the tools that Einstein developed in solving his problem, but now applied to the problem of quantum gravity. So that's the hope, and I feel like the idea is a good one, but I also haven't made as much progress as I hoped I would. I'm still really stuck on some very basic problems here. So, so that's the big goal. But yeah, it turns out physics is difficult.
Do you see any potential avenues through which your causaloid structure and other theories of quantum gravity, such as string theory, loop quantum gravity, and others, can interrelate?
Yeah. So I think it's possible that these approaches are complementary in the following sense that the causal approach and the other things I've tried to do are really coming from this sort of operational point of view, whereas string theory and loop quantum gravity start by positing mathematical structures that are motivated by more fundamental ideas, like what the fundamental constituents of a space time and are made out of. So you could think of it as trying to build a bridge between two shores. And, you've got the operational shore on the one hand, which is where you're looking at what you actually see experiments, and you've got this sort of fundamental shore on the other end, and you're trying to build a bridge between the two of them. And the hope is that the two things can meet up in some sense in the middle. So that's an optimistic viewpoint. It may be that the two bridges are built and they completely miss each other, and end up you end up with two bridges, which wouldn't be such a bad thing. But you want at least one way of thinking that works. So yeah, that's possible. I haven't interacted with the string theory community so much, at least so far as these ideas are concerned. Um, I've been interacting more with the loop quantum gravity community. There's an initiative funded by Templeton. It's called the Quantum Information Structure Space Time Initiative, and people like Carla Ravelli and Laurent Fidel are involved in that, and so we've been having meetings. Um, I mean, this is interfacing people who are working on quantum foundations, pursuing sort of ideas like the ideas I've been pursuing, and people from the quantum gravity community talking to one another. So I'm hoping something good will come out of that. It's still early days, I think.